Okay, let's look at section 11.2. We're looking at vectors in the plane. So velocity, acceleration, speed, displacement, and distance are where we're going to concentrate our efforts today. And if it will help if you think back to Calc 1 when we looked at objects moving along a line. That could have been horizontal movement, or sometimes we even had vertical movement. And same type of thing. We will start with a position function, go to velocity being the first derivative off position, and acceleration will be the second derivative off of position. It will be easiest if you continue to think of those relationships as we move into vectors. And just think of vectors as separate linear models. We're going to have, you know, the x component, x of t, and we'll have the y component, y of t. And then we can get its velocity by going x prime of t, and x double prime of t will give us our acceleration in the x direction. Y prime of t will give us velocity, y double prime of t will give us acceleration. And so then we can form these into vectors very easily. So shouldn't be too bad. I think it's a nice carryover from before. There are a few things to find like we just had talked about. Speed is the one that's going to be kind of unique. Speed is still going to be defined though as the absolute value of velocity. But in order to get that, we will use the formula, the square root of x prime of t, quantity squared, plus y prime of t. So the velocity vectors of each of the components and then square them each. That we know is really representing magnitude of our vector, and that is analogous to speed. Anything else? Oh, another thing sometimes referred to as the norm of the vector. I'm giving you another handout that has the same type of information, but I think it's a little bit clearer to read it. And you'll notice here that talks about, whoops, let's move down to the bottom here, about total distance traveled, still considered the integral of the absolute value of the velocity function. This is one where you get one value, and speed is the other one where we will come out with one value. All the others you're going to see have two components to them. Two values, two values, two values. So S bar is our position vector, V bar our velocity vector, A bar our acceleration vector. Let's do a couple problems. So a particle moves in a plane so that its position at any time greater than 0 is given by the position vector sine of t comma t squared over 2. Find the position vector of the particle at any time. Well, it has the same components as this position point had. So we can say we've got sine of t comma t squared over 2, and I'm using the chevrons to indicate it is a position vector. And then I'm going to have S of t, and then let's put a bar on that. So there's our position vector. Find the velocity vector. In order to get to the velocity vector, S bar of t, oops, t there, we can take the derivative. So it's going to be the x prime of t, comma y prime of t, which is really going to be what? Cosine t, comma, 2 comes down, cancels, comma t. There's our velocity vector. And then go on to acceleration, which we're going to want to play off velocity, aren't we? So the acceleration vector a of t, put a bar over top of it. We will be looking at the second derivative off of position and the second derivative off of position for the y value. And I'm going to just refer to above, and let's take another derivative. So we're looking at negative sine of t comma 1. describe the position in motion. Let's get our position function at 6, our velocity function at 6, and the acceleration vector. So position S bar of 6 will look like, need that, it'll be sine of 6 comma t squared divided by 2, 6 squared divided by 2, 36 divided by 2, we could call 18. Velocity vector will be v bar of 6, and that will be the cosine of 6 and 6. Okay, my pen is frozen up. So what I'm going to do is I'm going to just save this and then continue on with part 2.